Welcome back to my talk, An Academic Roadmap to Supply Chain Excellence. I'm Warren Powell. This is part 2 on optimal learning. Now, optimal learning is a name that I use for an activity that we all engage in, and we've done it pretty much since we were age 2. I like to also call this intelligent trial and error. There's a lot of other fancy names. These all mean the same thing, which is I have a set of choices and I want to find which choice is best. Okay, so these choices can be anything. I can have a small number of choices. I can have a large number of choices. But what almost always happens with these choices is I'm not actually sure how well each of them works. I have this degree of uncertainty. And so what I need to do is to find out which one is working best for me. And sometimes I have to do that by just trying it. Now, we may try this, in real life where we have to live with the performance of each of the choices. I may have a test environment, a laboratory, or a computer simulation, so what we call an offline learning. But either way, I have to run a test to learn something. This is often called in certain communities the multi-armed bandit problem. Let's imagine I have a number of slot machines, and we're going to pretend, this is absolutely not true, but we're going to pretend that each of these slot machines have a different winning probability. And the only way for me to learn the winning probability is to try the slot machine. Of course, as I try the slot machine, I get very noisy responses. I may have a high winning probability slot machine, but then I try it and I lose. So what we're going to do is to do it intelligent trial and error. Sometimes we also call this stochastic search, and I'm going to come back to this example. I might have some tunable parameters. These might be discrete. These might be continuous. These might be parameters to run an algorithm. These might be parameters in a trading policy in Wall Street. These might be choices I have to make in a manufacturing process, which I'll illustrate in a little bit. The thing is that when I run an experiment, I get a noisy response, and this is what makes this hard. Otherwise, I could just hunt and peck and try to find that red peak where things work the best. But because I get these noisy responses, I have to try to guess where the best is in the presence of noise. Many applications of optimal learning, tuning computer simulations, laboratory experiments where you're testing various materials and concentrations, manufacturing process optimization. This is a very big deal in semiconductor manufacturing, but pretty much any manufacturing process runs into these. Internet applications, bidding for ad placement, recommender systems which recommend what product to advertise, mechanical design of device, finance. Wall Street is full of trading packages that have tunable knobs. Trucking and logistics, optimizing prices and fleet sizes and bids, managing people. Strictly within supply chain management, there's a whole host of very specific decisions that involve having to do trial and error. And sometimes you can have a computer do this. Sometimes you have to do it in the field. And it runs across all the gamut of supply chain questions. Now, there's major problem classes. The first is how expensive the experiments are. They're inexpensive experiments that take microseconds to seconds, maybe minutes. For example, internet applications where I want to decide, hey, how many ad clicks do I get by promoting this one product? And it happens very quickly because I get a lot of clicks even within a minute. Then there's expensive experiments where you can take an hour to a day or a week, maybe a month to run one experiment. I can create examples where it takes a year to get one data point. Now, there's offline learning. This is where we're doing the experiments in a lab, in a computer simulation, some sort of test environment. We only care about the final design. We don't care about how well we've done along the way. Then there's online learning where I have to do it in the field. And so I have to, say, try out different prices or different drugs on a patient. And then I have to live with the bad outcomes that actually happen. So this is a very rich set of problem settings that really impact how you would go about solving the problem. Let's take a nice revenue maximizing problem. Let's say I have a simple, I think demand is a downward sloping line. Higher the price, the lower the demand. This implies a nice simple revenue function where there's an optimum price that maximizes revenue. And what I might do is if I keep aiming at the price that maximizes revenue, I'm going to keep trying out prices right there in the center. Now, the problem is I might not be very sure about what the true demand curve is. It might be any one of these dashed lines. And let's say it might be one of these dashed lines, I don't know which one. For each of these dashed lines, the revenue curve looks completely different. The optimum price is completely different. And being off of the optimum price, if I guess at the wrong curve, I could really be earning quite a bit less revenue. So the best way to learn the line is to try prices at the endpoints. That's the best way to learn the line. But as you can see, I'm not going to make very much money. So if I'm doing this in the field, which revenue management, you tend to have to do this, I'm not going to make very much money. Now, what I'd like to do is try out what I call the shoulders. In other words, don't do the optimum, but don't do the extremes. Do something that's just off the optimum. This allows me to do a much better job of learning the line while still making a good amount of money. Now, here's another problem. Let's say I want to advertise a product, or maybe I have limited shelf space. I have to pick the best product. And I'm a company with 7 products. I have baby products. I have kitchen products. And I have people, demand is very correlated among the baby products. People who like one of my baby products tend to like other ones. Same thing with the kitchen products, but not necessarily across baby and kitchen products. Now, I might have 7 different products, and I want to know which one works the best. I might give product G a crack, and I put product G out there on the shelf, or I advertise it on the website, and lo and behold, I get a nice bump in the revenue. It's higher than I thought. So in other words, my initial estimate isn't very good, so I go ahead and update my belief. I bump it up. Because of those correlations, I can bump up everybody else as well. Now, these correlations almost always happen in real problems. In all of my work in optimal learning, I've actually never found a problem where it doesn't happen. Now, what we can do is, how do I decide what product to try next? Well, here's 3 classes of what we call policies, okay? Now, in each of them, I have a point estimate. That mu bar is my best estimate of the performance of product X. Now, I also have another term that gives me an idea of the uncertainty, and there's different ways of doing this, but let's just call them some measure of uncertainty. And then I have a tunable parameter, and I take my best estimate plus the tunable parameter times my uncertainty measure, and I create what's called an index. And then what I do is I just compute this for each product X and find the best one. Very simple policy. Now, this is an optimization problem. It's a sort, okay? It's not a very complicated optimization problem. I create these indices and I sort them. So let's take a look at this middle one, interval estimation, which happens to be one of my favorite, partly because it really works quite well. Now, what we're going to do is, if I set that tunable parameter equal to 0, that means I'm just going with what I believe. So if it looks like product E is the best, I'm going to go with product E. Now, if I set that parameter theta equal to say 2, that's like going up what we say called 2 standard deviations. It goes up to the upper tail. Now product G looks better because I have a lot of uncertainty. Now, product G could not only be quite a bit better, it could be quite a bit worse. So you might say, well, wait a minute. I mean, it could be a lot worse. Why would I do that? Well, trust me. It actually turns out it works better to be optimistic. So now we have an optimization problem. What should the tunable parameter be? Now, I have a curve off to the right. Now, this curve measures what's called opportunity cost. Smaller is better. If I set my tunable parameter theta IE to 0, I get a high cost solution. This really doesn't work well. I don't want to do theta equal to 0. Now, if I do optimize it, boy, I get a much better solution. It really does work well. Looks like a number between 1.5 and 2 is going to give me much better results. Now, I want to introduce another way of solving this problem called the knowledge gradient. I'm very proud of this method because it came out of my lab. I had a series of students who developed this. Here I have 5 choices and 4 looks best. And so we say, okay, 4 looks best. That's the best decision right now. If I have to just stop right now, 4 looks best. Now, let's say I go over and try 5. I try 5 and I give it a try, and guess what? It doesn't work that well. My estimate does go up, but not enough. 4 still looks best. So I didn't change my decision. What's best is still 4, no improvement. Well, what if I go and try 5 and I get a big bump, and all of a sudden now it looks like 5 is best? Well, I look at how much better that is. That's my improvement. This is something that we're going to call the value of information. Now, the reality is, back there when I still think 4 is best, and I'm thinking of doing 5, I'm saying, hey, what if I do 5? I don't yet know the outcome. I don't know the outcome, and it could be any one of these random outcomes. Now, it turns out when you do the statistics, there's going to be a fairly high probability that when you go try choice 5, you're going to get an observation that when you update the belief, it's no better. You didn't improve anything. 4 still looks like your best. No value from doing the experiment. And then there's going to be some experiments that will come out better where you'll say, oh my gosh, I didn't realize 5 actually is better. So there will be a certain probability of no improvement, certain probability of some improvement. Take the expected value and you get the value of information from the experiment. We call that the knowledge gradient. Now, you can compute the knowledge gradient for every choice. Even if you have dozens to hundreds to tens of thousands of choices, you can compute the knowledge gradient. Now you have a number for each choice, and I'm going to pick the one with the best number. So here's a case, manufacturing, really big deal here. Manufacturing really has to work, especially semiconductor manufacturing, has to work on tuning the process. For example, I might have the diameter of the wafer, and there might be a certain temperature of a heating process, and I've got to tune the two to maximize the yield of a semiconductor chip. And by the way, maximizing this yield is a very big deal. This is what has determined the winners and losers in manufacturing this today, which, by the way, because sometimes at the level of which country will win, this is a very big deal. Now, what I've done here is I've discretized diameter and temperature into 50 increments. So I now have a 50 by 50 grid, about 2,500 different combinations. On the left there is my initial estimate of what I think each of the points will be, and it starts off just constant. I just say, I don't know what it is, it's just a big constant. Now, what I've done here is I've already done 4 experiments, one at roughly each of the corners. On the right is the knowledge gradient at each of the 2,500 points. Now, notice, I've got 2,500 points. I've only done 4 experiments. I still can create an entire surface for all 2,500 points. That's because of the correlated beliefs. Now, when I do this experiment here at this corner, look at what happens as a result of that last experiment. Okay, so the surface on the left didn't really go up or down, so no great discoveries there. But on the right, this is after you do the experiment. This is the knowledge gradient for the whole surface, each of the 2,500 points. And after I do an experiment there, the knowledge gradient drops, not only just for that one point, but for all the points close by. Once again, that's the correlated beliefs at work. Now, what I'm going to have to do is look at all the remaining surface and say, who has the highest knowledge gradient? Okay, pretty much it's flat there in the middle, but let's say that one is the optimum. And if I choose that one to do, I'm going to come over to the left and I'm going to run that experiment. Turns out it really didn't change anything again. You know, I didn't really learn very much. Now, over on the right, once again, that knowledge gradient in the vicinity of that experiment entirely dropped. Now it's saying, okay, I've still got this ridge left here, try that. Well, this time when I try it, I get a bump. I'm like, oh my gosh, I found something. Okay, where do I try next? Now, it might be tempting to stay in the vicinity that new, but the knowledge gradient says, nah, I've got this other bump over there. It could be out there. That is where the highest value of information is. Now, it turns out that's not a good place. And so what happens is we start reinforcing that surface. Notice I've now done 9 experiments. I have 2,500 different combinations of diameter and temperature, but after 9 experiments, I've pretty much got it. And by the way, I discretized 50 by 50. If I had discretized 100 by 100, I still would have gotten the answer in about 9 or 10 experiments, okay? So this is a very powerful logic. Also a little bit more complicated, a little more sophisticated, a bit more advanced math. Let's go back and compare this to our interval estimation policy. So our interval estimation policy, we have this tunable parameter, okay? And we can see that we get the best value. Now, by the way, getting that curve is not very easy. Here's the knowledge gradient. Now, the knowledge gradient does not have a tunable parameter. It's a much more sophisticated policy. one of the things you get is no tunable parameter. But this really surprised us in our research. If you really tune the interval estimation, it actually ends up outperforming knowledge gradient. Now this absolutely blew us away, but there's a lesson here. If you have a well-designed, sensible, simple policy that's properly parameterized, because that's when you do simple, you almost always get a parameterized policy. If it's properly tuned, it can work really well. It can work even better. Now, it's not much better than knowledge gradient, but the fact that it's better at all is sort of a head scratcher, because look at the interval estimation policy. It's a simple sort that you put in a spreadsheet, and updating it from one iteration to the next is really quite easy. Knowledge gradient is a more sophisticated policy. It's got a little bit more advanced mathematics, but the benefit, no tunable parameters, but that interval estimation can still work well. So interesting lesson here. Now, there's an entire spectrum of learning problems. I've just described learning problems where every time you do an experiment, the only thing you carry from one experiment to the other is what you learned. There are problems that also have physical resources, like I had to set up the machine or I have certain inventories, and I have mixed problems. So there is a wide range of these problems, but this is a problem that absolutely everybody encounters. Okay, once again, if you want more information, this is optimal learning is just one special case of a sequential decision problem, and optimal learning can be part of a very rich family of sequential decision problems, and this is where more information can be found.